viewers, welcome to CEC lectures. Myself Dr. Preeti Jagwani. I am from Department of Computer Science, Aribhat College, University of Delhi. So in this series of lectures we are learning introduction to programming using C++, and in the last lecture we have learnt about virtual functions, which is actually a mechanism to implement runtime polymorphism. Now, how runtime polymorphism is being implemented with the help of virtual functions is basically that we are taking one version of the function, or we are we can say defining one function inside the class base preceded by the keyword virtual, and the redefinition of that particular function with the same prototype is actually given in the derived classes, and these derived classes are inheriting the base class. Now within the main function we have taken the pointer to the base class and the objects of the derived classes and base classes as well, and then we have kind of tried to access that virtual function with the help of these we can say the pointer to the base class. Now what was the underlying principle there? That the kind of object to which your pointer is pointing to will determine which version of the function is executed. So for example, the pointer is pointing towards the object of the class base, the base class version of the virtual function will be executed. If the pointer is pointing towards the towards the object of the derived class 1, and then we are accessing that particular function, then derived class 1 version of the function is executed, and so on and so forth, and this determination is actually made at runtime. So this process is setting the baseline or setting the we can say platform for runtime polymorphism. Now one question comes in mind, that can we call or can we access a virtual function in the normal manner? In the normal manner means just by using it with using it through a dot operator by an object's name. Yes, we can do it, but this will not give the effect of runtime polymorphism. For example, so that means it will not give you the base for this virtual function's actual implementation. You can call a virtual function in the normal manner by using an object's name and dot operator. There is no syntactical mistake into that, but it is only when access is through a base class pointer or maybe through a base class reference, then only runtime polymorphism is achieved. So basically, if we are saying that we have one object of the kind of function, the object of the class derived 2, and we are trying to access d2.vfunc, it is also going to call derived vfunc, but calling a virtual function this manner does not take the advantage of virtual nature of vfunc. Although there is no harm in calling a virtual function in this manner, and it is also not wrong, but it will not take the advantage of virtual nature of vfunc, which for which we have declared it in the base class as vfunc. So till this point we have seen that this whole mechanism can be attained with the help of a pointer. Now at each and every point, whenever I am trying to say something about a pointer, I am also insisting on the we can say on the word reference, because this whole situation can also be attained with the help of a base class reference. In the example which we have discussed in the previous lecture, a virtual function was called through a base class pointer. We have taken a base class pointer and virtual function was being called for different versions depending upon which object that base class pointer is pointing to. But the polymorphic nature of a virtual function is also available when we access that function using a base class reference, because if you can recall, when we have studied pointers or when we have started with the term references, this was insisted that a reference is an implicit pointer. Inside it is acting as a pointer as well, or we can say it is implicitly a pointer. So whatever kind of, we can say, mechanism is implemented with the help of pointer, that can also be implemented with the help of a reference. So a virtual function can be called through a base class reference. So here what we will do, base class reference will be used to refer to an object of the base class or any of the object derived from that particular base class. So this is similar to pointer, as pointer to the base class was qualified to point to the object of the base class, as well as it was eligible to point to any of the object derived from that particular base class. Similarly, a base class reference, we can say, can be used to refer object of the base class or object of its derived classes. And when a virtual function is called through that base class reference, the version of the function executed is determined by the object being referred to at the time of call. Please recall our last lecture in which it was very categorically specified as well as seen through an example that when a virtual function is called through a pointer, the version of the function executed will be determined by the object which is being pointed to at the time of call. Similar thing goes here. When a virtual function is called through a base class, the version of the function to be executed is determined by the object which is being referred to. And the most common situation in which a virtual function is invoked through a base class reference is when the reference is a function parameter. We can use reference as a function parameter as well. This we have already seen in our previous lectures, and that's the most common situation in which we are invoking a virtual function through a base class reference by using reference as a function parameter. Now let us try to see the example of virtual functions using the reference to the base class. In the earlier lectures we have seen this whole thing using a pointer. Now let us see this using a base class reference. So base class reference will be used to access a virtual function, and within this program we have similarly created one base class which is having one vfunc, and it is declared as virtual, and within that it is printing this is base vfunc. After that we will be declaring two classes which are derived 1 and derived 2. These derived 1 and derived 2 both are both are inheriting the base class, and along with inheriting the base class they are giving their own versions of vfunc which was declared as virtual in the base class. So void vfunc in the derived 1 says this is derived 1's vfunc, and void vfunc inside the derived 2 says this is derived 2's vfunc. So till this point this program is very or we can say completely similar to the earlier one, but within the main function there will be some changes, because this time we are not banking upon the pointer, instead we are trying to explore the reference. Now when we want to use a base class reference parameter, as I have just told you that we will be using the reference as the parameter, we are using one function which is void AF, and within that function we are passing the reference of the base class, which is base %r, and using that r we are trying to access vfunc. And now please notice the use of dot operator here. Here we have not written r arrow operator vfunc, we have written r dot vfunc, because r is not a pointer. Arrow operator we will use whenever we are talking about the pointers. Here r is a reference to the base class, so when we are using references, it will be the functions will be accessed by using references through dot operators. Now within the main we have three objects. One is object towards the base, object for the class base, another object for the class derived, and third one is object for the class derived 2. So base B, derived 1 D1 and derived 2 D2, three objects are here, and now we are trying to pass these objects to the F. So, and that F, please recall, is having base class reference as the parameter, and within that F we have passed a base object to F in the first statement, which says f of B, then we have seen f of D1, and then we have taken f of D2, and finally our main is coming to end by return 0. Now what will happen? After creation of the objects, whenever that object is being passed inside the function f, for example, let us take the statement f of B. This f of B is going to call this particular function, and here the parameter which is being passed is base class reference, and that B will fit into the base %r, and the version which will be called will be the version of the base class, because we have passed the base object to F. So that means this will print this first statement which says this is base vfunc. Then after passing derived one object to F by saying f of D1. Now this f of D1 call will be resolved by using this particular statement and then void f, and within the base %r the actual parameter which will work is D1. So with D1 that vfunc will be called, that means the derived one version of the vfunc will be called, which says this is derived one's vfunc as we have written in the cout statement. And for the third statement, in which we are passing a derived 2 object to F, it will say this is derived 2's vfunc. So if you can see or if you can compare this program to what program we have gone through in our previous lecture of virtual functions or in our first lecture of virtual function, the output of both the programs will be kind of as it is similar. The only difference here is how we have implemented it. The earlier program was implemented by using a pointer. That pointer was of the class base. Here instead of pointers we have used reference parameter, and that reference is also out of the base class. So the program produces the same output as the preceding version, because in this example the f defines a reference parameter of the type base, and inside main function the function is called using objects of type base, derived 1 and derived 2, and inside f the specific version of vfunc that is called is determined by the type of object being referenced when the function is being called. Inside f, the specific version of vfunc which will be called will be determined by the type of object being referenced when the function is called. In the earlier, it was on the basis of your pointer and the pointer and the address to which the pointer is pointing to. That is determining which vfunc is to be called. Here, it will be determined by the type of objects being referenced. So, the two programs are producing the same output. The only difference is the mechanism, or the only difference is of the way in which it has been attained, because I have already told you that the reference is also an, we can say, implicit pointer. So, till this point in this lecture we have seen how to attain basically virtual function mechanism using references to the base class. Now coming to the we can say next remaining part of the lecture, if we can see this whole process of virtual function till this point. So, we are talking, every time we are talking about this is kind of runtime polymorphism, or we can say this is late binding or this is early binding. So, first of all, let us try to understand what is this binding, and then we will see where this virtual function category is going to fit. So, in order to explain the process of binding in C++, we can say the process of conversion of identifiers. What identifiers I am talking about? Variables, performance names, functions into addresses. Whatever identifier is there, that is being converted into address, and this process is basically known as binding. And for all for whom we are going to bind, the binding is done for each variable and the function. Whatever variables and functions we are using in our program, binding is done for all. So, for function, it means that matching the call with the right function definition, and for the variable, it means linking it to the correct address. Now, if we are talking about matching the call with the right function definition, this matching of call function call to the right function definition can happen at at 2 points, or it can happen at 2 places. One is either at the compile time or at the runtime. So, basically on this basis we have 2 types of bindings in C++. One is an early binding, which we can say is we can say compile time binding. Another one is late binding, which is runtime binding. So, early binding is achieved with the help of function overloading or operator overloading, and these 2 topics we have already seen in our previous lectures in this series. And now we are going through the process of studying the mechanism of late binding, which is achieved with the help of virtual functions. So, if we try to compare this early binding, which is also known as compile time polymorphism, and late binding, which is also known as runtime polymorphism. So, let us try to explore early binding some in detail. As the name indicates, the compiler, or it could be linker, directly associates an address to the function call. This is what your binding is. It replaces the call with a machine language instruction that tell your computer to go to the address of the function, and by default this binding happens in C++ in an early manner in the sense at the time of compilation. If we are not going to use any specific keyword like virtual, that means we are focusing on the compile time polymorphism, or in other words we are focusing on early binding, and early binding is a mechanism which is happening in C++ by default. If we want your compiler or linker, if we want these to be instructed for late binding, that means in that situation we need to take the help of the virtual keyword, or we need to take the help of virtual functions. Coming to late binding, or we can say runtime polymorphism. In runtime polymorphism, the compiler adds the code that identifies the kind of object at runtime. This is being done at the runtime, that compiler is going to add the code that identifies the kind of object at runtime, and the object which will match the call with the right function definition, and this right function definition is achieved with the help of this keyword. This we have already seen in our, we can say, previous lecture. So late binding or runtime polymorphism, in this process the compiler adds code that identifies the kind of object at runtime, then matches the call with the right function definition. Obviously this is also done at the runtime, and this can be achieved by declaring a function as virtual function. Now one thing also comes up in the mind, that what is the difference, or what are all the differences between overloading and virtual functions. So here we can say redefinition of a virtual function by a derived class sometimes appears similar to the function overloading, but actually it is not. This is not the case, because the term overloading is not applied to the virtual function definition. There are n number of differences, because there is the first and the primemost difference is of the prototype. In virtual function, prototype will be the same, only the definition is going to be changed. So prototype for a redefined virtual function must match exactly the prototype specified in the base class. This differs from overloading a normal function, in which return types and the number of the parameters, type of the parameters may differ, or more stringently we can say, while overloading a function, either the number of the parameters or the type of parameters must differ, otherwise your overloading cannot happen. But this is not the case with the virtual functions. So C++ can select the correct version of an overloaded function when there is a difference between the prototype of the overloaded functions, when only the name is similar. But when a virtual function is redefined, all aspects of its prototype are preserved, in the sense all aspects of its prototypes must be the same. If the prototype is changed while defining the virtual function, it will not simply be considered as, it will simply be considered as overloaded. It will not be in the category of, we can say, runtime polymorphism, and its virtual nature will be lost. So if a prototype is changed when you are trying to redefine a virtual function, the function will simply be considered overloaded by the compiler, and it will no more be considered as a virtual function. Its virtual nature will be lost. Now one more important thing here is late binding or runtime is done in accordance with the content of pointer, while your early binding. Now here it could be pointer or the reference. So late binding or runtime binding is done in accordance with the content of the pointer, that is location pointed to by the pointer, and early binding, which is compile time binding, is done according to the type of pointer. Because of the restriction and differences between the function overloading and virtual function term redefinition, sometimes this virtual function mechanism, that is virtual function redefinition by a derived class, is also we can say termed as overriding. So in this lecture we have attained how this virtual function can be attained with the help of reference parameter, as we have seen in the earlier lectures that how it is going to be done with the help of pointers. In this lectures we have seen how to attain this with the help of reference parameter, and also we have seen the detailed of the differences between the runtime polymorphism, that is your late binding, with the compile time polymorphism, that is overloading, or we can say early binding. And here is a list of references which is being used for the preparation of lecture. Thank you.